Alright, here we are on the back of the page. You got the Pac-Man problem, one of my personal favorites. I'm trying to move this so you can see the whole thing. So, read this drama to yourself, like many couples today. Mr. and Ms. Pac-Man get into quite a few arguments. Occasionally, here's one of the clips from their arguments. Ms. Pac-Man says, "Dear, you will need to mow the lawn and clean the garage this weekend." And Pac-Man, of course, as a tough guy, responds, "Oh yeah, maybe you need to stop yapping your big mouth." Ms. Pac-Man is insulted by this, says, "My big mouth? Look who's talking. You're the one with the big mouth." It's a very good argument. And of course the question this is really being asked here is, who's got the bigger mouth? So if you look at the shape of both of these two Pac-Man figures, now you know what those shapes are called. Those shapes are called sectors. Think about the two things you're going to need as given information. How do you find the space of each mouth? And it's not the distance of opening the mouth, it's the space of each mouth. Hopefully you're thinking, oh, I need the degrees on there. That's one of the things I need, the measure of the arc. So Ms. Pac-Man can open to 50 degrees, Mr. Pac-Man can open to 30 degrees. So it looks like Ms. Pac-Man might be bigger, but I also am going to put the radius on there. Mr. Pac-Man's radius is 4 inches. Ms. Pac-Man's radius is 3 inches. So kind of a balancing act going on here. Bigger radius, smaller degree measure. Smaller radius and bigger degree measure. Figure out these two areas. Good time to pause. Run some calculations on here. This one I'm going to show only in terms of a decimal. So give you a minute or two, try that out. Maybe pause it and then go for it. So if you're back checking it out, I think these are two areas you end up with. Mr. Pac-Man just slightly larger than Ms. Pac-Man. He's a little bit over 4.19 square inches for area. And Ms. Pac-Man 3.93. So you know, Mr. Pac-Man does have a big mouth, as you can see on there, just slightly larger than Ms. Pac-Man. Alright, give you a second to draw these two. This is a very common core question in math, especially next year. They're going to see stuff like this all the time. You got a triangle inscribed inside of a circle. In other words, the triangle's corners are on the edge of the circle. And it's not just a boring triangle. It obviously, if this is 60, and that's 90, you know that's 30, so it's a 30, 60, 90 triangle. Don't get confused about this 10. The 10 is between the dot and the edge of the circle. So the 10 is the radius. This entire diameter would obviously be 20. And you can go with trig if you want on this. I suggest you use ratios. You know, hopefully you know this is going to be 20. You can find that one and that one. I want you to find the yellow space on here. And looking, you can probably see it here. The yellow space is down here. There's also a tiny little sliver of space over here on the left. So you're trying to find the entire yellow space, which is basically this entire semicircle. That dot, it usually means it's the center of the circle. So this is entire yellow space minus the triangle that's white. And we'll go to the peace sign after we finish this one. So you might want to pause and try to go for this on your own. You have enough information there to solve this thing. It is a tricky one. It's finding the segments of a circle, two segments of a circle. It's a little trickier than usual, but it's really using area addition or area subtraction postulate to find it. So that shaded region is half a circle or a semicircle subtract a triangle. Hopefully you can work out the calculations on here. Area of a triangle is 1/2 base times height. Area of half of a circle is 1/2 pi r squared. Radius, of course, is 10. So 10 squared is 100. Half of 100, this is going to be 50 pi. The base and the height, you've got to either use trig or use ratios. So hopefully you know that if this is 20, the little short leg is going to be half of that. This is going to be 10. And of course, this is 10 rad 3. And if you were to do a decimal, 10 rad 3 is approximately 17.32. So do some calculations on that. You know, I like to leave my answer in terms of decimals. I think you end up with somewhere around 70 square units. Kind of tilt this up so you can see a little better. 70.4 square units is what I get for an answer on that. So that's sort of an upper level question, a little harder question on there, but hopefully makes sense. And as you can see, the peace sign information popped up there. This long segment that goes through here is a diameter. And you're going to see, you have to make that assumption. I'll just tell you that's a diameter. These little pieces here are all radii. So I'm just going to give you that up front. So you have 1, 2, 3 radii up top. You have a radius on the bottom. And the entire way through, you could call that a diameter. So the 7 meters is sort of, it's a huge peace sign. The 7 meters is this radius on the bottom. 135 degrees is the arc on the right. Again, you might want to pause. Try this one on your own. Find each color on there. So find the yellow, find the green, find the red, find the blue or magenta or whatever the heck color that is up top on the right. Hopefully end up with 57.7 square meters for yellow space. If this is a little trick you're going to get good at later on. If this is 135, you've got to realize that's a diameter. And a diameter is actually cutting a circle in half. So this entire circle over here is 180. Sorry, this half circle is 180. So you're going to have to subtract 135 from 180 to get this little blue piece over here, which would be 45 degrees. So to get these blue and red, these are both going to be 45-degree arcs over here, which is just because this is a diameter cutting the circle in half. So I think you end up with around 19.2 square meters for that space. And of course the red and the green correspond and are congruent to the right side of the circles. Hopefully that makes sense. Alright, last problem, and one of my favorite problems on here, is the darn goat problem. Some of you know about goats. Goats are known for their destructive nature. And if you let them run free all around the yard, they'll just chew and destroy everything. So old MacDonald ties his up to the corner of his barn. So he's got a barn, he's got a garden in the back, and he wants to kind of calculate the area of destruction on here. So I'm going to give you some dimensions. His barn is a 40-foot by 25-foot rectangular barn. His garden is behind the barn, is a 30-foot by 10-foot garden. And there are no fences around his garden. He didn't have time to put up a fence this year, so no fences around the garden. So this goat might be able to reach into the garden here. And of course that would all depend on the length of the rope. The rope is a 30-foot long tether, a 30-foot long rope, and he's tied to the corner of this barn. So if you haven't read it yet, maybe pause, read the question, see if you can make sense of it on here. This is the type of question you have to think about a little bit to really get the hang of it and understand how it relates to everything else on the previous slides you've been looking at here. What's the total area of destruction, and how much of the garden is left unscathed, and how much of the garden does not get touched? So if you haven't figured it out yet, the space that the goat's going to destroy is everything. He's going to get everything over here, everything over here. If you were to start shading that in, eventually you would shade in something that's very circular in nature. Now, I'm making the assumption he can't chew through the barn. Maybe they have some Kevlar covers on the barn or something, I don't know. He cannot get into the barn and chew through the barn. He can get all the grass, all the anything that's out here, but he can't get inside the barn itself. So I try to drew that to kind of show you roughly to scale on here. If this is a 30-foot long rope and the barn was literally 40 feet long, he can't quite get to this corner. Maybe it's obvious he's 10 feet short of this corner because this entire thing is 40 and he can only reach 30 feet of that. Do the same thing on the top here and you'll see he can get into the garden. There's no fence here preventing him from getting in the garden. If this 30-foot rope were to turn, he could get a certain number of feet into the garden. And it relates to this 25-foot dimension. He can get 5 feet into that garden. He can just barely get around the corner. The rope would get stuck on the corner, and he'd be able to go around the corner and eat 5 feet into the garden there. And probably eat some raspberries or carrots, or I don't know, he'd eat anything. So I want you to find that basically the total area of destruction is all the yellow that you see there. It's two different sectors. It's this big one and this tiny little one. And you got to use some sort of logic on here. This is obviously hopefully a right angle at the barn. So how many degrees would this entire arc be, the big one? Hopefully, if that's 90, that leaves 270 for that portion. Or 3/4 of a circle. I'm already reducing this. 270 over 360 would reduce to 3/4. That's this huge yellow space. This little yellow space is just a quarter circle, or a 90-degree portion. So 1/4 of pi r squared. The radius on this section, of course, is quite a bit smaller. like we said before, if this rope is 30 feet long, this is 25 feet to the corner and gets 5 more feet. The radius of that little piece would be 5 feet. So this is the little quarter circle. This is going to be a much smaller portion on there, as you see when you run some calculations. This is only 6.25 times pi. The big space is 675 pi. So this is like 100 times bigger than that space. Add those together, and that gives you the entire yellow space that he's going to destroy. The second part of this question, how much of the garden is left unscathed? In other words, how much of this green garden is still going to be green did he not get to? Well, the original garden would be 10 by 30, or 300 square feet. And this little sliver we cut out here was the 6.25 we just calculated a minute ago. So this is the amount of garden that's still left over. That's in terms of an exact answer. In terms of pi, I believe that's approximately 280 square feet of garden space that's left untouched by the goat. In other words, that's all this stuff that's still green. The goat only got to that 5 foot into the corner there. So hopefully that makes sense. Kind of a tricky section, kind of a lot to it. You'll see we jump all the way to page 767 on the homework. You should probably start this in class. This is due the next day. This is due on Thursday. It's on Schoology already. 2 through 6, 9 through 12, 22 and 30. Not too bad of an assignment. I think once you get the hang of it, you'll see it's pretty easy. Good luck. You'll see 1 or 2 of these on the quiz coming up. And I'll be back on Friday.